Suppose 1 comma 2 in R. What is the smallest convex set containing 1 and 2? Pardon? Smallest convex set containing real number 1 and real number 2. Geometrically you can, pardon? Correct. Line segment between 1 comma, that means closed interval 1 comma 2. That's why there no difference between connected and convex. So here what is the convex set containing this unit circle? I mean unit ball. Okay. Here we sometimes what you say is correct. Some places sometimes we use unit sphere even for the set of all x as the norm x less than or equal to 1. Here we take unit sphere set of all x norm x equal to 1 boundary less than or equal to 1 unit ball. So because if you take any 2 point all these things will be there. You cannot remove the so unit ball you have to go. So convex, you see, further assume it is convex, then we can prove. Again, this we are going to prove for any Banach space. Here to start with this Hilbert space. Finite dimensional means no need of proving, already there. Prover's theorem, then infinite dimensional also Sauder fixed point theorem. So what is important here is it is just a closed bounded convex set. Okay. Yesterday also someone suggested the first day, then very natural thing is first can you give at least one example. Say that it is a closed bounded convex set but not a compact set. Closed bounded convex set but not compact. Can you give an example? In a Hilbert space, because we want to start with a Hilbert space. Later we will see for other thing also. I mean, that's what if you have revised functional analysis, it will be still easier. Even metric space knowledge will do. Closed, what you know that we know only one familiar infinite dimensional Hilbert space. Which Hilbert space we are familiar? More familiar? Which Hilbert space? Any one example? Pardon? Example of a Hilbert space. Finite dimensional even R is also, R is a Hilbert space, set of real number. R is a, what is inner product x with y? What is, don't say escape, usual. It should not be useful answer, no? Equal to what? Inner product, suppose order per x1, y1, one element. Order per x2, y2, then inner product is of these two elements. x1, y1 plus x2, y2. Okay, like that we know Rn. If it is vector space over R. Suppose if it is R itself. Just product. X in R, y in R, the inner product nothing but there x into y. Now in the beginning start y, the inner product means is x1, y1 plus x. There we stop with x1 real number, y1 real number, x1, y1. Okay, that Rn we know. That is inner product. That inner product will induce a norm. You can verify standard dot product. How? What is that norm? No, not in R alone. General inner product space. X vector space over R or C. Let us take over R, real vector space. So we know what is an inner product. Inner product, no need of recalling, no? Okay. X is X with an inner product is there, inner product space. That will induce a norm. What is that norm? Norm of X equal to using inner product. Using positive root of inner product x with x with x. If we go for even R2, we see that what do you mean by when y equal to x, order per x1, x2, order per x2, y2, then dot product is x equal to y mean again x1 squared plus x2 squared, that is nothing but Pythagorean distance or Euclidean. So, we can feel it, then we generalize. So, motivation come from symbol like either go to R or R2, then we will extend. We know that if x is an inner product, then we define norm x for each x in x, positive root of inner product x with x, then we can prove that it is a norm, and this norm is it always, will it be, whether it is complete? Every inner product will induce a norm. When that norm will induce a metric, d of xy equal to norm of x minus y. From vector space, we define a vector space, we know addition and scalar multiplication having some property. Then we have defined inner product. Okay, that will give the additional thing. So we can give the length as well as even angle between two vectors, all those things. Okay, now we got a norm, inner product. The next one, what is the question? Whether it will induce a metric, whether that metric is complete. That means whether every inner product, what do you mean by every inner product is complete? Mean the inner product will induce a norm, whether that norm is a complete norm linear space. Is it true? I am making this statement, every inner product space is a complete metric space. Say true or false? False. Then someone else. Give an example. Suppose x is, because we are more familiar only finite dimensional, then what will happen? If it is finite dimensional, then it is true. So, to give an example, that should all these things, functional analysis, all this advanced fixed point theory, all meaningful. If we cannot stop only with finite dimensional, you have to come up infinite dimensional. So then only it will be more useful. So can you give an example of a inner product space which is not complete? Even if you know an inner product space which is complete, from that also we can get a. Okay, can you give an example of an inner product space, infinite dimensional which is complete? Either you give inner product space which is not complete, or give an inner product space which is complete. Familiar one is L2, little L2, capital L2 will, that is using measure theory. So first again we will call it capital X. This is very important. Each element is a sequence of real number xn n1 to infinity, so that each xn belongs to R, n1 to infinity, square summable, mod xn square n1 to infinity is converges, that is all. This is useful, converges. Okay. What is the here? This is our set x. For x1 element in L2, y another element in L2, what is inner product x with y? Summation n1 to infinity in this case. What is, see, finite dimensional means x1, x2, xn, n double, y1, y2, yn. There x1, y1 plus x2, y2 plus xn, y1. Here we will not stop. Summation, yeah, xn, yn, n1 to infinity. Whether it is meaningful to write this? I have written some summation xn, yn, or you call it xn, yn equal to an. So you call it summation n1 to infinity an, where an equal to xn, yn for all n. Xn real number, yn real number, so xn, yn is a real number. So what we got? Square also. First we are writing this section. We want to check whether this is meaningful. Summation n1 to infinity an is a series. So, but inner product is what? It is a function from x cross x to real inner product R. So that means image x is one element, y one element, inner product x with y we are defining as summation n1 to infinity x and yn. That should be a real number. That should not be infinity or minus infinity. It should converge. Why it converge? You have to verify. So you heard about, for these things are all non-trivial. While proving that there are some inequalities like Holder's inequality, using that Minkowski inequality, all these things, even to prove that it is a vector space. Later, see, we are directly writing, we also have to define x, L2 is only a set. Before proving, defining inner product, you have to verify that it is a vector space. Vector space, I mean again we will not spend more time. X equal to xn, y equal to yn, then component wise. X plus y equal to xn plus yn. Again alpha times x is alpha xn. Then we have to verify that it is a vector space. For that itself, you have to x is in L2, y is in L2. Then you have to prove that x plus y again L2, that will be easier. Then while proving norm or inner product, you need some other Minkowski's inequality, Holder's inequality, like that. Like Schwarz inequality in finite dimensional case. So this you please go through. So we know, we can prove that this is an inner product space. Under this, then the norm, L2 norm we call it, this is very important for us. Norm x suffix 2, we call it summation mod xn square n1 to infinity. Here it is easier, mod x is in L2, that means summation n1 to infinity mod xn squared finite. This series converges, that means this is a real number. Real number means finite, fixed, positive real number. Then we can take the root. That is what the length of the vector x. Then you can prove that using Minkowski's inequality, means nothing but triangle inequality, but to prove that you need Holder's inequality, that it is a non-linear space, or you can satisfy parallelogram law, or from inner product you come, then we can prove that it is a metric space. So that itself non-trivial. I mean, proof is not difficult. Again component wise we will do. If you take a Cauchy sequence xn, here one xn is a superscript, x1, x2, I mean the sequence will be x1, one element in L2, x2 another element, like that. So x1 means, we write it x1 1, x2 1, xk 1, kth element, like that. x2 means x1 2, x2 2, like that, xk 2, like that. Like that here nth term and mth term and distance between xn and xm. That means then you will prove that each component, this column, they converge, because we are, if you start with the Cauchy sequence, then we will prove that for each fixed k, the kth column, xk1, xk2, that is a Cauchy sequence in R, that converges to an element xk. So like that you will get x1, x2, xk dot dot. Then we have to prove that that is in L2, and the original sequence xn converges to this x1, x2, x3. Same idea will use whether it is in L2 or LP, 1 less than or equal to p less than infinity, L infinity. Okay, what is L infinity? For us, these two things more important. L infinity instead of this, just it is a bounded sequence. Then what is the norm there? There it is not a metric, norm, it is a metric, it is not an inner product. Note that inner product space will induce a norm, the norm will satisfy which law? Parallelogram law. Like L infinity, even 1 less than p less than infinity, they will not satisfy parallelogram law. So inner product will become only when p equal to 2, that is complete, that is Hilbert space. So, but L infinity norm is, that's it, supremum mod xn. Why we can take the supremum? Because it is a bounded sequence. Again we will go back to a bounded sequence, means it will have upper bound. It has an upper bound, lower bound. Here what we are interested is upper bound. Set of all mod xn, n 1, 2, 3 has an upper bound, hence by which axiom? One of you. LUB, least upper bound axiom. If a non-empty subset of R has an upper bound, then it will have least upper bound, that we also call supremum. Hence the supremum exists. This is simple exercise, including to prove triangle, no Holder's inequality or Minkowski inequality, then it is a non-linear space. Again it is complete. Complete also again the same idea will use. X1 it will be a sequence of the one element, mean one element in L infinity mean a bounded sequence. Then again like that, then each column you prove that it is bounded. That is almost simple. Each column, kth column is bounded and you will prove that if you assume that xn is a Cauchy sequence, mean again each column is a Cauchy sequence. Then we are in R. That's why completeness of R is at least that proof, that's why I repeat it even second time. R is complete, then each column will converge, then you will get x1, x2, x3, then you have to prove that that is bounded, hence it is in L infinity, then xn converges to that x. So hence L infinity, just some idea. So the reason I will tell why we are interested in these two spaces right now. Okay, now come back to our, now we are comfortable with L2. To start with, L2 is a Hilbert space, you can verify, it is a Hilbert space. Okay, now take the unit ball, whether unit ball is set of all x in L2, so that norm x of x2, sometimes I may just say norm x, L2 norm, less than or equal to 1, the unit ball in L2, that is closed, bounded, convex. So far our condition will be satisfied, closed, bounded, convex, whether it is compact. That's why giving example is not difficult. Closed, bounded, convex subset of L2, unit ball, for that matter, any closed unit ball in L2. Is it compact? If it is compact, what will happen? Oh, that's correct. We will come back to that. Some non-expert, okay. Some student function, no. What you are telling is correct. Example is correct. So even without you using that also, unit ball become compact in any norm-linear space. Suppose the unit ball set of all x in the norm-linear space x, so that norm x less than or equal to 1. Suppose that set is compact. Then what can you say about the vector space? What type of vector space? It is of dimension is finite. That is using, that is called Heinz-Borel theorem. That is functional analysis like Rn type. Finite dimensional means essentially it is isometrically isomorphic to Rn. It is like Rn type. I mean you can prove any finite, once the unit ball become Compact means the vector space will become finite dimensional, because functions maybe some of you will study little later, third semester students, that at least keep this in mind. If you are here, that's what, if you have any infinite dimensional vector space, there we have a norm. That means infinite dimensional non-linear space. Then the unit ball will never become compact, but it can become compact in some other sense. We define what is called weak topology. It may be compact with respect to weak topology. Weak topology, it may be little involved. The smallest topology on the non-linear space X, which makes every F belongs to the dual space continuous. We call tau omega. That is the smallest among all topology. Norm will induce a topology, that is with respect to that every F is continuous, F in the dual space. Dual space means set of all continuous linear functional. That is there. But there may be many norms. Among the norm, we have to prove there exists a norm which with respect, that is the smallest norm which make every F in X prime also continuous. That topology is called weak topology. Suppose a set is compact with respect to that weak topology, we call it weakly compact. Finite dimensional, there is no difference between compact, weak compact and compact with respect to the norm, topology induced by the norm. Okay? This here doubt mean you can please ask. This is little for students first time in. Any doubt? Pardon? Okay, first I will give you a simple application using Banach contraction theorem, then we will come back to our stated theorem. K closed bounded convex subset of a Hilbert space, T from K to K non-expansive, then it has a fixed point. That is called Prouder's theorem. Later Prouder and Koch, they proved the same theorem in place of Hilbert space. They assumed what is called uniformly convex Banach space. Okay, that I will explain, it depends upon the time. And the same year, Kirk introduced a concept called, he did not introduce the concept normal structure, that was introduced by Brodsky and Millman in 1948. Brodsky and Millman in 1948 introduced a concept called normal structure. See, normal structure means, see, suppose we are, okay, now suppose set is like this, convex and everything is here, symbol set I will write, okay, like this, need not be unit ball. You take a point here, any point, this is our set K, X belongs to K. From X is fixed. Then this we call it R of, sometimes the small r or capital R does not matter. X is fixed, then find the, from X find the distance to every point. Every point from here means everything is there. That means supremum of norm of X minus Y, Y varies from K. Okay? This we define for, we can define for every X. Why this supremum? Whenever you write something, whether it is meaningful, supremum X is fixed. Say I am here, say I am X. From X to every one of you I am finding the distance. Then I can find the maximum distance because finitely many. Here our set may be not finite, it is infinite convex set. Why supremum exists? Because our set K is bounded. Because of bounded, norm of x minus y less than or equal to some constant for every. So it has a upper bound, supremum will exist. I think in the beginning, for whatever we write, whether it is meaningful or not, we will check, then proceed. So supremum exists, and what is the diameter of the set? Diameter of K equal to supremum of, what is the, how we define diameter? Distance between any 2 points, then take the supremum. We should not tell maximum, because maximum no meaning if we do not know it may exist or may not exist. So this diameter of K, supremum of norm of A minus B, say that A comma B belongs to K. This also exists. Sorry. It may happen that what you feel that R1 for each x, see, even in simple thing you take, closed interval 0, 1. Our set K equal to closed interval 0, 1. I am taking a point, say let us say half. What can you say about delta of half and K? That's why I tell you first, even the teacher doesn't have time to spend so much time, because you have to complete the syllabus, to do so many examples, extremely simple. See here what is our this say, in this case our x equal to half, y varies from where? Y may be this side or this side, anywhere. What is the maximum? In this case maximum x is supremum. What is that? Delta of this is equal to half. What is the diameter of K? Diameter is 1. So half is less than 1. That means, suppose if we take the point itself 0, suppose x is 0, what is delta of 0 comma K? 1. That is equal to diameter of K. Okay? But there are points, in this case enough point, any interior point, there is an x, so that delta of x comma K is strictly less than diameter of K. See, essential idea of this is what the geometrical structure introduced by Proudski and Millman to prove some fixed point theorem, not in 65, 1958. They proved it, the family of isometry map. Each member in that script F, a collection of map from a weak, okay, you take it easier mean closed bounded convex subset of a, say, Hilbert space. But Hilbert space we should not use Banach space, because Hilbert space we can prove that it has normal structure. So you can take X Banach space, K compact with respect to weak topology, K some type of compact, or even you assume that it is compact, K compact convex, script F a collection of map from K to K, say that norm of Tx minus Ty equal to norm x minus y. Every map there it is an isometry map. Compact convex, we have a family of map, and then under want to see that can we find a x in K, one point which will preserve every element in, that means there exists x in K, such that Tx equal to x for every T. Suppose T1 is in S, T2 is in the collection script F, T1x equal to x, T2x equal to x, T3x equal to x, like that. Common that family will have a one point which is preserved by, fixed by every member. So that type of result long back, that's a Proudski and Millman proved. That using that time they introduced normal structure. You can easily verify that, not very simple, it is not, if it is a compact convex subset of a Banach space, yes it has normal structure. Meaning is You take K, I will not write everything,